Hey everyone, welcome to this conversation that I had with Professor Michael Strevens, a philosopher of science at New York University. Michael is a great communicator of science and the philosophy of science. And in fact, as I told him, if anyone does ask from me about the philosophy of science, so what really is science, I would probably give them his book, The Knowledge Machine, and tell them to read chapter one because it thoroughly covers this great method debate between those like Thomas Kuhn and Karl Popper as to what science is. And it was a fascinating conversation. We spoke about, yes, the social structures of science, all the way from that to human subjectivity, to AI, and what it means to be a subject in a universe ostensibly of objects. But put more formally, as I said, Michael Strevens is a philosopher of science at New York University, primarily working on complex systems, scientific explanation, the social structure of science, and philosophical applications of cognitive science. And just on this note, in fact, he said that the current project he's working on is on cognitive development, more from a philosophical angle, and that's certainly is kind of super interesting. And outside of academia, he is perhaps best known for his book, The Knowledge Machine, in which he explains why science is so successful at creating knowledge and why it took so long for humans to figure out and how to do it right. So, saying all that, without further ado, here's my conversation with Michael Strevens. Firstly, Michael, thank you for making time for chatting with me. Uh, just to orient the listeners, perhaps we should probably start off. It's quite interesting your career transition. You went from studying computer science, you did a bachelor of computer science, and then you transitioned to studying mathematics, and afterwards philosophy of science. So, what made you go down that path?
Well, it was probably a lot of accidents at the time, but looking back, it makes complete sense. Uh, I think that what I discovered in the course of moving from actually physics and computer science through mathematics all the way to philosophy was a kind of a inclination towards thought at the most abstract and foundational level. So if I'd become a physicist, I probably would have been working on the fundamental laws of nature as a particle physicist or something like that. And if I'd become a mathematician, I probably would have been sucked into category theory or some grand set of unifying principles. But in philosophy, whatever you do, you're thinking those thoughts. And there was just something about that I guess I realized I didn't so much want to spend my time kind of chipping away at the rock face. I wanted to stand about a million miles back and see how everything all worked together.
Mm.
Philosophy seemed like the ideal vantage point for that.
Is it more like you wanted to give yourself quote unquote permission to ask the grand questions that philosophers have asked since time immemorial?
Well, I suppose it's more I wanted permission from the university. So
Fair enough, fair enough. Yeah, we're all part
for
of
that
it.
to count as my research and
Yeah,
not just my secret hobby that I practiced
yeah,
at night and on weekends
yeah.
under an
Interestingly,
assumed
I
name.
believe I think a person that you look up to quite a lot, Thomas Kuhn. You mentioned him a lot in your book. I believe even he studied physics and then transitioned to more of like history of science and philosophy of science. So that really this is the question that I want to start off with more at a high level. The reason being, I've realized if anyone's going to ask from me from now onwards, what is philosophy of science, or can I have a bit of a brief introduction? I just tell them to read chapter one of the Knowledge Machine, because one of my favorite chapters where you go through the kind of the history of, well, really 20th century science and this quote unquote great method debate. So I'd love for you to, Michael, maybe like expand and lay down. We've probably done this many times in previous podcasts, so I apologize if you gotta repeat yourself. The debate between Karl Popper and Thomas Kuhn, and
Mhm.
what's this ongoing great method debate in the philosophy of science?
I think it all began in when a lot of intellectuals in the 20th century were looking at the mess that the human race had made of, or at least the kind of the European part of the human race had made of the world, and this is actually particularly after the First World War. That's why I'm emphasizing Europe, and decided that what they needed to do was to rebuild everything on rational principles. And at that time, that really meant scientific principles for them. And so this question came up: what are scientific principles? What is it to go about, for example, constituting a state scientifically, or drawing up a moral code scientifically? And those are deep, complicated questions that I don't have answers to, and I wasn't writing about in my book. But of course, it turned all of these philosophers into philosophers of science. They had to say, here is the right way to go about gaining knowledge, the scientific way, as opposed to the other way. So they wanted to be able to write down, in effect, some rules for inquiry. Not necessarily a complete guide to inquiry, but some kind of set of rules that was distinctive enough to separate science from all the rest. And what I call the great method debate begins there, with the attempt to say what the scientific method is in a way that differentiates it from all other forms of inquiry. And after the early difficulties in doing that turned into a big debate about whether there even was a scientific method. And you can see one way to look at Popper's and Kuhn's work is this: that Popper was someone who thought he knew what the scientific method was, and he is a paradigm of one of these thinkers who wanted to make the world scientific. He wrote, and he did write on politics as much as he did on science. But anyway, he's someone who believes there's a scientific method, and he can tell you what it is, and that the right sort of critical, rational, scientific mind is the one that applies this method. And probably more than anyone else in the history of, at least in the history of 20th century philosophy of science, Thomas Kuhn is identified as someone who undercut Popper's project. But Kuhn is not a negative philosopher. He has his own, actually quite sophisticated story about how science works, but it's really deeply different from the kind of the standard method story. And in fact, it's a story in which scientists don't come out looking like these kind of critical rationalists, but something rather different. And we can talk a little bit more about that in a moment, but rather than diving into it, I just really want to stress this contrast between, on the one hand, this single scientific method that's the epitome of critical inquiry with Popper, and then with Kuhn, there's a distinctive social organization in science, but it actually involves many different methods at different times, so there's not one unchanging method. And furthermore, that setup is almost, you might say, if not irrationalist, then there's many elements to it that seem quite at odds with Popper's very heroic view of scientific inquiry as I say, the apex of rationality.
Yeah, I mean, after all, Popper was also a political philosopher, right? I mean, I've read his book, The Open Society and Its Enemies. The book on totalitarianism, and he even calls Plato the person who started all of totalitarianism. So it's quite interesting. Professor Strevens, if we could start with Popper, and then of course the unfalsifiability principle. Now, anyone could, I don't think it's that hard, even for a layperson like myself, to just Google what it means and get a very elementary understanding. So perhaps you could firstly just explain what the Karl Popperian unfalsifiability principle is, but then also, as you've done in the book rather well, maybe lay down some of your criticisms of it, just for the audience.
Yeah, sure. So Popper thought that really the heart of the scientific method was this very simple idea that if a theory makes a false prediction, it has to be wrong somehow. And Popper thought at the core of scientific inquiry was the systematic elimination of all of the false theories. And notionally, of course, you could imagine one day having eliminated them all and just having one true theory remaining, although, as Popper was understood as well as anyone, that was not a realistic prospect. But he thought we could at least think of ourselves as making progress by eliminating the false theories. So the thing that makes that... Oh, go ahead.
No, I was just going to ask. Please continue. I want to kind of follow up on that, but keep going. Yeah.
Okay. So the thing that makes that, though, now turning to where he begins to run into difficulties, and yeah, he had plenty of things to say about these difficulties. It's not as if this is some sort of one-shot undermining of his view, but it's really difficult when a theory does make a false prediction to figure out whether it was really the theory's fault or not. Science is such a complicated thing, and in particular, the kinds of measurement apparatus that are used to make observations in cutting-edge science are often very complicated, fragile things that only work when conditions are exactly right. 99.9% of the time, when you get a false prediction, it's not really the theory's fault at all. It's just that something went wrong with the apparatus, or maybe you made a false assumption when you were making your calculations, or maybe even, and this does happen, there's an error in the software that you're using to analyze your results. And so it's not really the theory's fault or not. And it would be a terrible mistake to throw away the theory just because you got this false prediction. So if you're going to capture the spirit of Popper's proposal, you have to figure out some way of deciding when it's okay to just say, oh, something went wrong with the apparatus, and when you should say, oh no, this time it's the theory's fault, and so we've falsified the theory, as he says. We can throw away the theory. Sometimes, of course, you can just see that something went wrong with the apparatus, like, it's smoking, making crackling noises. Yeah. But often in many cases in the history of science, we have results that were anomalous and looked like they caused problems with theories, and we'll never know what went wrong because it's just too late to go back and check. I'm sure we'll probably end up talking about some examples later on, but this Popper really never fully satisfactorily answered this question of when it's okay to blame the apparatus or other assumptions and when you should blame the theory. I think he had interesting substantive things to say, but he didn't succeed in writing down what he was really after, which was a kind of a systematic calculus, if you like, for making these decisions, something that took these decisions out of the hands of scientists who might be indulging in motivated reasoning, trying to see their own theory in a good light, and just sort of said, no, you must follow this logic, and this logic says your theory is wrong.
Yeah, because I haven't read his book where he introduced the principle, what's it called, the logic of science, I believe, but
logic of scientific discovery, it's called.
That's it. Yeah, I haven't read that book, although my understanding, again, at a very elementary level, is that it seems that Popper really wanted some kind of a priori principle or even theory of science that allows scientists to do science. And then what you would argue for, and many others, would be that, oh, well, unfortunately, for better or worse, let's say, we haven't found that.
Yeah. And so what you in fact have is, I kind of made it all sound more like a philosophical argument, but the fact of science is you have real arguments over these things, whether probably a result is just an artifact of some problem with the measuring apparatus, or the theory really is in trouble. In fact, that's almost more normal than any other state of affairs. So typically the scientists who perform the experiment will trust the apparatus more than the scientists sort of a few labs over who weren't there to kind of see it all operating and so on. And in the end, if scientists keep going for long enough, there does seem to be a kind of a consensus that forms. The experiments get done enough times by enough different people. It's not as if we're just totally at sea, but it doesn't have this simple, crisp, objective, algorithmic feel to it that Popper was really reaching for.
Yeah. Well, I guess that leads us to, I don't know if I should call it the antithesis, but at least let's say, we'll juxtapose Thomas Kuhn's theory, the paradigm shift, the term that he popularized, with the Popperian principle. So the Structures of Scientific Revolutions, perhaps my favorite book on philosophy of science. Yours is a healthy contender.
I'll take that.
So in contrast to Karl Popper, Professor Strevens, how does Thomas Kuhn differ? Because he came after Popper, isn't that right? So and what were his views? Yeah.
So Popper wrote his book in the 1930s, and Kuhn wrote his book in the 1960s, to give you some sense. So Popper is in a way essentially interwar, I suppose we would now say, and Kuhn is very much post-war.
Yeah.
And Popper was still kind of firing on all cylinders by then, but he wasn't presenting whole new ideas. Well, he was entitled to kind of have a break. So Kuhn's idea is actually, it doesn't dispense with the idea of a scientific method, as I was saying earlier, but rather the idea is that at any particular time period, a science, say like particle physics or molecular genetics or economics, maybe microeconomics, will have a particular method, a particular set of rules for doing science, and actually a rather comprehensive set of rules for doing science. But that these methods are not fixed for all time. In fact, they change in episodes from time to time in dramatic episodes called scientific revolutions, or the phrase that Kuhn famously popularized for this is a paradigm shift. And the paradigm here is this kind of big method for doing science. And when it shifts, that means the old paradigm has crumbled and a new one comes along and replaces it. So whereas Popper and the sort of classic searchers for a scientific method were looking for a single rule that is valid for all time, as you said, hopefully a priori, one that we can just know is right with certainty. Kuhn thought these methods only last for a while, and then their scientists actually push them to the point where all of their flaws are exposed, because they're very rich, but they're also kind of limited. They have a lot of assumptions built in, and inevitably some of those assumptions will turn out to be wrong. And so scientists push them to their breaking point. And in effect, they destroy their own methods by exposing the faulty assumptions or whatever. And then some new method has to come along and supplant the old method. A new paradigm comes along and supplants the old paradigm. That's a paradigm shift. That's a scientific revolution. Then you have a whole new methodological complex governing what scientists do in whatever area of science it is.
So in this way of paradigm shifting, would it be, because it's not fair to say, like, for instance, from the Newtonian worldview of classical mechanics, let's say, to now with quantum theory, quantum mechanics, is that really a paradigm shift, or is a paradigm shift something where we have like an epochal, something like from Aristotelian science or physics to what we have in modern science? Because the reality is we still, despite living now in the paradigm, let's say, of quantum theory and quantum mechanics, we still subscribe to certain Newtonian principles, for sure, right? And it's not like we've completely dismissed that. So how did, perhaps maybe like flesh out a bit more what really is a paradigm shift?
Yeah, well, I think the change that is most central and to a paradigm shift, although it's not the only change, is a change in a kind of a whole theoretical conception of how the world works. So although on the superficially quantum mechanics or equally Einstein's general theory of relativity, so that the kind of the successor theory to Newton's work on gravitation in particular, although that preserves a lot of what Newton said in the sense of making the same predictions, the theoretical underpinnings look really different. So I'll do it with gravity. In Newton, there's this force that objects with mass exert on one another. They pull one another, and that's gravity, and it causes them to accelerate, and as spelled out by Newton's second law. But in Einstein's theory that replaced Newton's theory, there's no force directly between objects like that. Instead, objects impart this twist or curvature to space-time, and then other objects are trying to travel through that space-time, but because it's twisty, they themselves take a curvy path, which is just the path of, say, a body like the Earth orbiting the sun. Anyway, I probably shouldn't try to explain general relativity any further. But the point is, it's even though it makes a lot of the same predictions as Newton's theory, which it had better do, because Newton's theory made so many correct predictions. It's a really different way of thinking about what's going on. And that's kind of at the core of what makes it a new paradigm. But it suggests all of these new experiments that just wouldn't make sense in Newton's theory. So an example of that would be looking for the existence of gravitational waves. Einstein's theory predicts, because mass actually has an impact on space-time itself, when you have especially very dramatic events like two colliding black holes, will actually cause space-time itself to shiver, like throwing a rock into a pool. You get these waves that ripple outwards. So you should be able to detect those if you build a sensitive enough apparatus, which physicists finally succeeded in doing in about 8 years ago. I mean, they've been building it for about 50 years, but it finally detected gravitational waves in 2015. So you get all of these new ideas about what you might do with science. And that's characteristic of a paradigm shift. It's not just a set of new theoretical ideas, but all of these new ideas for actually doing science, new kinds of experiments or observations you could perform. So that's what makes that shift from, you mentioned quantum mechanics, and I kind of subtly changed the example just to gravity, because it's I think a bit more straightforward.
Yeah, the principle stands, yeah.
But the idea is it's the new paradigm manages to do on the surface, superficially, in terms of prediction and so on, a lot of what the old paradigm did, but gives you a whole new picture of the way the universe is working that makes sense of those predictions.
Yeah, in fact,
your method for doing science suggests all of these new experiments you might do and so on.
Yeah, I was thinking of like a more of a contemporary example of this, and I realized I'm reading this book also by Tim Maudlin, the philosopher of science, on quantum non-locality, and there's an interesting kind of story of Einstein, because John Bell he mathematically proved quantum non-locality, I believe in the 80s or 90s. And then Tim Maudlin, he's like one of his, John Bell is like one of his heroes. And then I believe in the Nobel Prize in Physics was awarded to the laureates who proved quantum non-locality, it's a mouthful, experimentally. And then in the book, he talks about how Einstein didn't want to accept this idea of non-locality, because his theory was in fact local, and he called it spooky action at a distance. But then, of course, now that we have mathematical proof and empirical evidence, let's say, which kind of sticks to your iron rule of explanation, it seems like we're kind of going through that paradigm shift where, well, I guess physics isn't local anymore in the way we thought. And I find that endlessly fascinating, how it just completely shifts not only our theories, but just even at a very existential level, how we view the world and experience the world.
Yeah, that's a great example of a paradigm shift where you get this new kind of fundamental theoretical apparatus, quantum mechanics, and that makes these weird predictions about non-locality. And so it suggests all of these scientific experiments you might do that wouldn't have made any sense in Newtonian physics. And in particular, those Nobel Prize winning experiments that really established that the predictions of the theory really were accurate.
Yeah. All right, Michael. So this is again the iron rule of science, of explanation, which you introduced in the knowledge machine.
You can just call it the iron rule of science.
Of science, right?
Looking back, maybe I should have just called it that. It would have been quicker for everyone.
Fair enough.
Let's just call it the iron rule.
Yeah, although what I loved about this is because I've been trying to kind of develop this idea on my own too. Firstly, let me see how I can formulate this question. You mentioned how for Kuhn, in many ways, this scientific paradigm, it's kind of something we could never step outside of. It would be like speaking another language. Like we're within the language that we speak and experience the world. But then you argue, using one of your heroes and one of mine too, Newton, that no, in fact, in the private lives of a scientist, they could speculate, step outside. Newton was into theology and alchemy, and he had his own curiosities. But then this iron rule is kind of, what was that? Sorry?
I said even philosophy.
Oh my God, even philosophy, yeah. But the iron rule is like this kind of public, the public face you put on for like a very crass term, I guess. But And I thought, yeah, that's what science is, and perhaps that's a good thing. Like I love that people are still allowed to do whatever they want to do in their private lives, but then in like a public institution, there is this rigid rule to be followed. So yeah, sorry, I talk too much, but maybe you could expand on that, the iron rule of science, since you gave me permission to say that.
Yeah, so we started out talking about these thinkers who wanted to say what it is to be scientific.
Yeah.
And in a way, Popper and Kuhn each have their own stories about what it is to be scientific. This is my story. And the idea is it's not so much following a certain set of rules about figuring out what to think on the basis of the evidence. I mean, scientists do that, but I think there's no fixed set of rules that every scientist has to follow. So in their own heads, as you're saying, there's all sorts of things going on. And Newton's head, there are an extraordinary abundance of ideas, some of which seem not very scientific at all. But then when Newton comes to write down his ideas, that's when he follows the rule. So the rule is like, I think at one point in the book, I call it a speech code. Okay, it doesn't legislate in any way how you're supposed to think, or even what you're supposed to believe on the grounds of the evidence. It just regulates the way you can talk about it. And what it says is that when you're writing your results up officially for other scientists, so writing articles in scientific journals basically is the way that works these days, whereas for Newton it was above all writing his big book, the Principia on the theory of gravitation. But when you write that stuff down, all that you talk about is the empirical evidence, and it's the way it fits with the hypotheses or theories that you're advancing or testing or criticizing or whatever. So in a way, it's something, I mean, this idea that the public product of science, the communications of scientists are just all about empirical testing, that in a way is actually a pretty familiar idea, I think. I mean, it better be if all scientists are following this rule. But my suggestion is that it's, but you might think that, that's not, the important thing is what goes on in scientists' heads, why they believe what they believe, not how they write their stuff down. When you write a scientific article these days is a sort of a standard order, for example, in which you tend to go through you have this kind of setup, background, methods, outcomes of the experiment, and so on. But so what? You have to do, it's all pretty well organized, but that's kind of a sideshow. That's just sort of like having nice, neat typography. But I think it's actually much more important than that, because these forms of communication are in effect the only way that scientists can present their results for posterity. I mean, I suppose you could, we can dig up Newton's notes and so on, but the thing that's actually printed and put between two covers and circulated and so on has to be put in this form. It means that doing science becomes all about empirical testing, because that's the only thing you can talk about. So the iron rule is saying you can only write about this stuff, and that alters the whole character of scientific research by making it directed towards things that will be useful in these, I suppose you might say, literary products. I mean, just the journal articles and so on. So one way I talk about it sometimes is it makes science almost, or at least, it makes science into a kind of a bit like a game. You have all your own reasons for believing the stuff you believe, and some of them may be quite unempirical. But when it comes to actually writing down your official argument, convincing your colleagues and so on, it all has to go through empirical testing. And so that makes it crucial to actually do a lot of empirical testing. Otherwise, you'll have no moves to make in the game. So it focuses all of the energy of scientists onto just this kind of one form of argument that's based around observation or measurement or testing or experimentation. And I think that actually we're used to the idea that science looks like this, but actually science didn't look like this until Newton came along, basically, until the 1600s. The way it used to look was much more like, Aristotle, the philosopher Aristotle. So certainly there was plenty of stuff about explaining the observable data and so on, but there was also a lot of philosophical synthesis. There might have been the introduction of considerations, kind of a unifying urge, a desire to have a certain kind of elegance to theories and so on that scientists still adhere to, but none of that stuff goes into the actual publications. So you look at Aristotle and you find, the theories that are supposed to make sense of what we observe around us, but very much mixed up with philosophical reasoning about the way the world has to work. Whereas Newton showed a way, even he himself, who had all these philosophical beliefs, managed for some reason to just put them aside and say, I'm not going to worry about any of that stuff. I'm not going to be caught up in these arguments, for example, about how the ultimate foundations of causation, about whether all causation has to be by kind of contact, by collision, or whatever. All I'm going to do here is write down a set of mathematical principles that make the right predictions about gravitational phenomena, that make the right predictions about how bodies like the moon will orbit the Earth and the Earth orbit the sun, that will make the right predictions about the trajectory of a cannonball that you fire into the air and so on. And I'm just going to call that science. And that it turned out to be enormously successful to forget all the philosophical stuff, which is what the iron rule is telling you to do, and just try to get the phenomena right using a bunch of principles, and often in science, mathematical principles. So the iron rule, by saying just all that matters is getting the phenomena right, in the case of in Newton's sort of science, just making correct predictions, really changed the character of empirical inquiry without necessarily changing what was going on in people's heads. It changed what they had to do in order to get into print.
So is this why, Michael, you argue in the book that this sounds like heresy for us general people, that science is in fact not a humanistic discipline? It's rather irrational, as you put it.
Well, it's a very narrow thing. So, as I say, the scientists themselves doesn't have to be narrow to get involved in doing science. They can be, as we know, Newton was not narrow, because we've seen his unpublished papers when they came to light, and we've seen, for example, he was engaged in got quite interested in these philosophical disputes about the nature of space or the nature of causation, and wrote ripostes to Descartes and stuff like that. But he never published that stuff. He kind of, it's like he set himself the iron rule. The first scientist, really, I think, ever to do it and stick to it. And he left all that stuff out. But the result is that he's left a lot of his thinking out, and a lot of his reasons for belief out of what he writes. So there's a sense in which he's not really, neither he nor anyone who follows the rule is giving you all of the reasons for believing the thing that they're trying to urge you to believe. And so there's a kind of there's a gaping hole in the rationale that's provided in scientific writing. It works really well to motivate scientists to just focus on this empirical task of getting the predictions right, because that's all they're allowed to talk about. But it leaves out a lot of their thinking. And then that sense that kind of takes the complete human and cuts lots of pieces out of the human thought, and just leaves one particular kind of thought.
Yeah, and that's for me
what
kind of
I
like,
think of as being not humanistic, although very effective.
Yeah, because what's interesting is, like, it's kind of like almost like a sublime paradox, where Newton, by restricting himself, paradoxically opened himself up to the Newtonian revolution, and that's, who would have thought that would be the case. Whereas, in fact, I think in the book you argue that if you go and propose the iron rule of explanation to, let's say, Aristotle, he'll be like, "No, man, what are you talking about? Of course, I'm gonna philosophize and ontologize. I want to think about what's causality and whatnot. Why would I not?" And so it is rather out of place for a person who's interested in big ideas to tell them, no, just narrow into just empiricism and whatnot. But Michael, here's a few technical questions. I know you called it an iron rule, But then as I was reading your book the second time, I realized it comes off in many ways. I think I feel that it viscerally like it's more of like a practice, because it's not like some kind of objective a priori principle that everyone follows. It's rather a practice embedded within the institution of the public institution of science. So is that how you would portray it?
Yeah, that seems exactly right. So it's
Yeah.
You put it as well as I could.
Yeah, fantastic. Alrighty, I have heaps of questions. I have a few like speculative, more like grand philosophical questions that I'd love to ask from you. But before that, and I'm sorry, Michael, you already did this in a couple of episodes, I know, but please, if you could humor me with, it's a very, very fascinating story where you cover the Eddington experiment, Arthur Eddington, where they finally prove Einstein's theory of relativity. It's just an interesting piece of history of science in the 20th century. You probably repeated this story multiple times. So again, apologies. But yeah, do you mind kind of explaining the Eddington experiment and then how that sits along, I guess, how that story becomes a part of this ongoing debate on the philosophy of science?
Yeah, totally. So I'm happy to do that. And it's a great illustration of some of the issues I was talking about earlier.
Exactly.
About how complicated it is to interpret the evidence. So Einstein formulated his theory of relativity, his new theory of gravitation, in its final form in the middle of World War I. And there he was, a German scientist on one side of this war, which eventually came to an end. And there on the other side was an English physicist, actually a pacifist, Arthur Eddington, who was a real Einstein fan. I mean, of course, this had nothing to do with the conflict. Eddington just thought that Eddington was a really good mathematical physicist, and he saw the beauty and elegance of Einstein's theory and was able to appreciate the mathematical complexity of the theory. He was able to understand the theory in spite of its mathematical complexity, is what I should say. And Einstein himself had realized that one thing his theory did was made a prediction about the degree to which gravity would bend light rays.
Light rays, yeah.
And that prediction was different from any kind of prediction you could get out of Newton's theory. I mean, not that Newton himself was making such predictions, but, with the kind of modern estimates of the mass of light particles and so on, you could get something along those lines. So Eddington realized that you could test this prediction by taking photographs of the stars very close to the sun during a total eclipse of the sun. Now, the only reason you needed an eclipse is so that the sun is blotted out. Otherwise, you wouldn't be able to see the stars. But because the stars are close to the sun, their light's going to be bent, relatively speaking, quite a lot. Although actually, it's not that big. That's not very much bending as it kind of passes close to the sun. So the idea is to do this experiment, or really it's an observation, not an experiment. We take telescopes to where a total eclipse is going to be and take photographs of the stars right next to the sun and compare them to the same stars without the sun, and you'll see an apparent difference in their positions, from which you can just immediately, in a very straightforward way, calculate the amount of bending, and then you can just compare that to what Einstein's theory predicts and what Newton's theory predicts. And if you get the number that Einstein's theory predicts, then it looks like Einstein is right, and you've come up with a whole new kind of evidence for this novel theory of gravitation. Anyway, so Eddington created, with the help of a bunch of people, of course, an expedition that actually went to two places in the course on the trajectory of the eclipse. And one of those locations, the weather was much better. Actually, the location where Eddington wasn't. And they had two telescopes there. And they got conflicting results from these telescopes. One telescope gave results that actually matched Newton's prediction pretty well, and the other one matched Einstein's prediction much better. So what do you do in a situation like that? Well, it turned out that the Newtonian results, so the telescope that gave you the results that look bad for Einstein. The photographs were a little bit blurry, so something had gone wrong with the apparatus, but not so much that you couldn't calculate a bending angle. But what had gone wrong? Nobody really knew. Eddington and his team said, well, it could be that everything's just a little bit out of focus, but we can still get the numbers, in which case Einstein would be in trouble. Or it could be that something had created a kind of systematic distortion of the image, which actually would have shifted the stars in a way that might have exactly, as it were, canceled out the extra pull that's there because of the theory of relativity. So it might be that there's exactly the thing you want to measure, that is how far the stars look like they're kind of pushed out, has just been systematically messed up by this distortion, in which case the results of that telescope would be pretty much useless. But you don't know which it is. This is one of these questions about what do you blame? Is it Einstein's theory you should blame for getting this false prediction?
Or the equipment, yeah.
Or is it the equipment? Something went wrong with the equipment, but you don't know exactly what went wrong. And there's certain things that very plausibly could have gone wrong that still would have left Einstein's theory looking wrong. Of course, meanwhile, there's this other telescope that's much more helpful to Einstein, but it's all a bit of a mess, it seems. Anyway, in the end, Eddington and his team, without really giving any reason for thinking that there had been a systematic distortion, just dismissed those results and said, the really clean results we have, well, let's just concentrate on the really clean ones. And they all support Einstein, which, as it happens, was what Eddington wanted to happen. But some of the other physicists, including physicists who performed the same kind of experiments, so people who are specialists, in other words, in these kinds of measurements, were skeptical about this. And they thought, well, I mean, it's true that those results could be systematically wrong, but we're far from knowing that they're systematically wrong. We shouldn't necessarily treat them as though they have no significance whatsoever. So this is a case where, in reality, you have two groups of scientists who I think, they're both, of course, they're human beings, but they're also trying to do the best they can, just end up disagreeing on how to interpret the results because they can't agree on which bit of this complicated setup to blame. And maybe I should add that this mirror, which had caused the blurriness, hadn't caused any problems before the eclipse. And then when they went back and tested it again after the eclipse, it was working perfectly. So there was just no way, it's not like they didn't go back and try and figure out what had gone wrong, but they just didn't have the information.
Yeah, it was happenstance, and fortunately Einstein was right, in fact, but he could have.
Yeah, so now we can look back, and actually, one of those critics of or people who thought Eddington shouldn't have been so quick to dismiss the results that didn't look so great for Einstein, himself led an expedition to the next really good eclipse in Australia a few years later that really did a lot to cement Einstein's theory. So he got cleaner data than Eddington had.
Okay, I didn't know about
That's a good example of how you have a disagreement, but as long as people are not being totally unreasonable, those disagreements tend to get resolved. And I'm sure it helped that his name was W.W. Campbell, was actually doing the experiment with, he was right there in the place. It was his experiment. But also, you do the experiment more and more and you slowly eliminate various sources of uncertainty. You don't get any blurriness the next time around. Phew, maybe something else goes wrong, but then you do the experiment again at great inconvenience, because it's not easy to find an eclipse and you have to travel to out of the way places.
Oh, certainly. Yeah.
Science kind of gets there in the end, but not in this very methodical way where it's able to, as it were, make up its mind at every step of the way exactly how to treat the evidence. Instead, you have a whole range of opinion with different views about what might have got wrong that tends to converge over time, just because the more evidence you get, the more you kind of satisfy different scientists' suspicions or reasons for skepticism.
But this is excellent, because I think this perfectly leads us to this idea of how does science self-correct. It's not even something we do consciously, but it's kind of a part of that public institution, as you outlined. because it's interesting when Popper and Kuhn, when they were doing their work, especially Popper, it was, as you said, kind of like this, to try and find an answer as to where human beings completely got it wrong with World War II and all of that mess. And now I think this debate on the philosophy of science is perhaps most pertinent for our times, post-COVID, because as we all know, science became deeply a contentious political matter where, it's interesting how, and this is why I love studying the philosophy of science, because just in the general public, a lot of the criticisms that certain people like Anthony Fauci and all these other quote unquote figureheads of science, although we know no such thing exists, but just for, let's say, the public facing figures of science, whenever they self-corrected, whenever they said, oh no, masks work, masks do not work, yada yada, this was seen as a bad thing. But I would assume if we were following your iron rule of explanation, it's quite the contrary. This is exactly what science should be doing. But anyway, could you kind of expand on how does science self-correct, and why? I don't want to say we should blindly trust science, but we should probably understand that paradoxically, science works by its failure to work, if that makes sense.
Yeah, I think there's a sense in which it's just not true that science self-corrects. And there's a sense, but so I don't mean that science doesn't find the truth eventually. I mean, it very, very often does, and perhaps most of the time it does. Now that we've had a few hundred years of it, we can see this long string of successes. So it kind of tends to get there in the end, at least on the kinds of questions we've asked of it so far. But I think it doesn't get there by going back and fixing its mistakes. So take the Eddington thing. It's not as if we still don't really know what happened with that telescope. And we didn't make progress by figuring out what was wrong with it. We didn't make progress by reaching some agreement on what was wrong with it. So you'll actually find people arguing even today about whether Eddington should have disregarded that data or not. But not relativity physicists. They could care less, because since then, what's happened is, instead of those old experiments being kind of, as it were, corrected or cleaned up, they just kind of got submerged between more and more data that was better in various ways. Fewer things went wrong, or there's just sort of, the equipment became more reliable as people used it over and over again. They developed new techniques that eliminated certain sources of error. This tends to happen, and so what you have is not so much a kind of a complete understanding looking back of why all the experiments came out the way they did, but more, you have so much recent data that's quite compelling that you just stop worrying about all the old complications and confusions and mysterious results. So that it's really more a kind of a swamping process by which science makes progress. And something like the pandemic, where people are really, their lives depend, or at least it seems like they might depend on making sense of the science, really kind of brings you face to face with that element of science where there's can be quite a lot of disagreement on how to interpret the data, especially early on when it's not very good. It's as it was, say, with something like masking. So you have different scientists disagreeing with one another about the effectiveness of masking, using different techniques, putting their faith in different techniques. So some people were much more reliant on controlled experiments that had been done with masks that seemed to show they weren't as effective as you might expect. Other people were much more convinced by experiments that were sort of like mechanical experiments, which showed that a mask just would trap the great majority of the virus and so on. And it's not the case that all of this stuff, first of all, the public sees these arguments, these disputes, which just seem to be based on different subjective estimates of which source of information is more reliable. But then they also don't get to see some subsequent process where everyone explains why things came out the way they did earlier on. Instead, they see opinion shifting, but they don't really see the sort of the self-correction that some people claim exists, that might be responsible for that. that convergence of opinion. In fact, I would say, 99% of us now still couldn't really give a clear story about how the thinking about masking evolved over the course of the pandemic. And that's pretty typical of science. It's not so much self-correction, it's just sort of doing more and more empirical testing. And that's where the iron rule comes in, because that's in some sense, and so the iron rule really encourages you not to argue a lot, once you've kind of looked at the empirical data that exists on the page, as it were, you can't spend too much further time arguing about the significance of that data. The thing to do is to go and do more experiments. So the iron rule really encourages scientists to just pile layer upon layer of new data,
sure.
swamping the old data, and that's kind of how scientific opinion is formed much of the time, I think. Yes. So it doesn't really look like people expect science to look, which is a little bit like those 20th century, those noble 20th century figures, the way they expected it to look. It's not, you see science being made, and you don't see everyone kind of agreeing on what to think about the evidence. Okay, well, we're not sure yet, we just need a bit of this, bit of that, then okay, well, that means this, methodical, stepwise, and then backing up if there's an error, going back and saying, oh, we figured out what went wrong, okay, now it's all good from now on. Instead, you just see a kind of chaotic process that's mainly a sort of a headlong data production process, where just more and more evidence gets thrown onto this big unruly pile, until finally enough scientists declare themselves satisfied enough that some sort of consensus emerges. And that doesn't look methodical enough to be science. And yet that is pretty much exactly how science works.
Yeah, and case in point would probably be climate change, right? Because if you think about it, there's no such thing really as climate science. Like climate science itself are myriad amounts of sub-disciplines where scientists working in their own fields that probably don't even talk to each other, but they're working on their tiny bit of research, hopefully following the iron rule of explanation, and then kind of, I don't want to call it a synthesis because that sounds like they're all in agreement, but there's something emerges that, okay, this is the current hypothesis within these conditions that we put in. And most scientists would say, okay, look, climate change, it's a problem. We got to do something about it.
Yeah, and with climate change, you have a big solution to this problem, which is the UN body, the IPCC, which does try to synthesize everything. As you say, there's all these different people. There's people who work on the oceans, there's people who work on clouds, there's people who work on just putting things together into a big mathematical model, but they don't understand exactly why these are the right principles for clouds and these are the right principles for oceans. And it's in principle, it's a collaboration, but as you're exactly right to say that 99% of the time, scientists are just working on their own little bit of the story. So you need somebody to put it all together, but you also run into this problem of what I call the essential subjectivity of science, that you have a lot of disagreement. You have a lot of different rival principles or models, and it's with these different models of, say, clouds, for example, ways of dealing with clouds and models. You have the same kinds of disagreements you have with different measuring instruments. One group thinks their model is better, and the other group thinks their model is better. And eventually, hopefully, we'll figure it all out. But meanwhile, we need to make decisions. We need to know what to do about climate change. How much to spend and what way to spend on avoiding at least the worst outcomes. And so we don't have time to wait for the scientists to all say, okay, now we have enough data, we can definitely tell you what's going on with the clouds. Instead, you have the IPC is basically not just synthesizing the data, but synthesizing opinion and saying, okay, well, there's a spread of opinion about these models. We can't change the fact that there's not one agreed way to deal with this stuff. But what we can do is sort of average over that range of opinion. So if they do their job well, and some climate change skeptics worry that that's all a stitch up and they're not doing their job well. don't think that's right. But if they do their job well, then they're kind of at least finding the center of opinion and taking a kind of a snapshot, or taking the temperature, if you like, of the range of opinion about these things at the time, and delivering it up to policymakers so that they can actually make somewhat well-informed decisions about what to do. And that's an operation that actually exists outside of science as it's normally pursued. In most sciences, there's nobody doing that. There wasn't a group of arbitrators sitting there looking at the eclipse experiments back in 1919 to decide exactly which ones we should trust and how much, and saying, we're fairly sure that Einstein is right, or something like that, the sort of thing the IPCC says about certain levels of sea level rise. It would be too expensive and too complicated to have that. And in a way, you don't really need it. It's not urgent. And as long as the iron rule kind of sends all scientists sort of charging off back to the lab, back to the observatory and so on to bring in more evidence, then eventually with just a little bit of luck and a lot of determination and focus and funding, the picture will clarify. But there is a need with these things like the pandemic, with COVID, things like climate change, to have somebody that is very scientifically well informed but exists outside of the normal scientific structure to actually do this interpretation in a sort of real time, as it were. It's because science has this character that we've been talking about, that you can't just kind of, as it were, open up the scientific journals and see what the current state of knowledge is, because in a sense there's no such thing as the current state of knowledge, or at least there isn't. Insofar as such a thing exists, it's more like an average over a wide range of opinion, expertise, and so on. So it means that interpreting science is hard work.
Oh, certainly, yeah. And I'm so glad you mentioned, Professor Strevens, the essential subjectivity of science, because if someone just pushes you to a limit and asks, what is objective then in science, how would you answer that question?
You mean what's actually objective
in fact, yes. So like, I think in your book it's very clear that there is this essential subjectivity, and you've explained, you've given a few examples right now. But then if someone's like, okay, then tell me, in contrast to that, what really is objective in science? Do we even have objectivity in science?
Well, I think there's a lot of objective stuff. For example, the rules that you follow when doing a statistical analysis of data are objective. So you can just look at the data and see whether or not, assuming you have the time, but it's only a matter of effort. You can just see whether the analysis was done right, whether the right sort of rules were applied, and whether the mathematics follows through, and so on. The question of, out the other end, you get some kind of number, like a p-value, a confidence interval, or something like that. And it's completely objective what that interval is. What's really subjective is how to interpret what it's telling you about the theories you're interested in. So the objectivity, I think, is really important, but it only goes so far. And it doesn't solve this problem of deciding what to think. It's not doing the job that the IPCC is doing with climate science, for example. And in fact, and no rule could do that. So I would emphasize both the subjectivity and the objectivity. The subjectivity is the fact that in the end, no matter how we try to formalize, rigidify, and so on, the treatment of data, and it is important to do that, we're still, the interpretation of that data, in the sense of, but what should I believe given all of these results, is going to be subjective, meaning that reasonable, well-intentioned scientists who are not any more biased or prejudiced than any other human beings on this planet, they're going to end up disagreeing, as long as at the cutting edge, when the science is still being done, they're going to disagree on the significance of the data. One group's going to say this telescope is a big problem for Einstein, and another group is going to say it's not a problem at all, something went wrong, we should throw away that data. So that's the subjectivity, in some sense, is bigger than the objectivity. But the objectivity lies, I think, at the heart of the iron rules ability to lay down a kind of a set of rules for this game of just doing empirical testing. As you go back to it kind of tells you what kind of data to get and what kind of statistical processing to do on to that data, even if it doesn't tell you how ultimately to interpret it all.
Yeah, because it seems as if what you're saying is the objectivity of science isn't something you could sort of tangibly say, oh, that's it, that's the objectivity, but it's rather more like a meta rule or a practice, like the iron.
Here's one.
It's objective. Yeah.
Here's one thing you could say. I think you could say, if you just look at the scientific literature, the journal articles, that there's a lot of objectivity in there. So where you find the objectivity is in those articles. They're just reports of the data. I mean, not that stuff can't go wrong, or even sometimes you have scientific fraud, of course. So, but what I mean is, you'll see lots of objective rules that all scientists have agreed are the appropriate rules and so on being followed there, and you'll see a real effort to leave anything subjective out. That is, the subjective stuff will be omitted. So look at the journals and you'll see a lot of objectivity, but look into the heads of scientists as they read the journals and as they think about the evidence and the results and what might be promising lines of inquiry, and you'll see a lot of subjectivity.
Yeah. All right, Professor, if I may now, I would like to get some rather kind of more of the grandiose philosophical ontological questions, because given I have this opportunity, I want to make good use of it. So okay, the metaphysics within physics. I've been thinking about the iron rule, empiricism, and the idea of predictability. So what are your initial kind of metaphysical intimations on quantum mechanics or quantum physics? And then would you say that modern physics and even perhaps modern evolutionary theory kind of disproves this idea that all science is about is empiricism because of issues with predictability and whatnot?
Okay, so two pretty different questions, right?
I know. Yeah, sorry. I hope you don't mind. Yeah.
All right.
I mean, you could answer them individually if you want. It's fine. Yeah.
I mean, as far as what is physics telling us the world is really like? I guess I'm somewhat agnostic about those questions, but I have affinities, if you like. There's a sort of a kind of story I would like, I'd be happy if that kind of story turned out to be true, but I don't know that I feel confident enough to argue for it.
Yeah, I mean, this is purely speculative, which is kind of why I said that I would like to go there towards the end of the conversation. Yeah.
So I like the idea, so much of our science is statistical in the sense, not just that we do statistics, but we build these statistical models of the way the world works. So quantum mechanics has these probabilities in it. The statistical physics of heat basically has all of these probabilities in it. But I like to think that deep down the universe is deterministic. There's no probability. And that this probability stuff emerges from some very particular kinds of physical structures, kind of like the same physical structure you find in a coin toss, to take a very simple example. And that we can understand why these statistical theories are so fruitful ultimately by understanding the deterministic roots. Now, I don't know, we do have deterministic stories about the bottom of, what quantum mechanics ultimately rests on, and something like David Bohm's theory, or sometimes it's called an interpretation of quantum mechanics. I don't know if that's the one I would ultimately be hoping for myself, but I don't really have any alternative to offer. But that it does this kind of desire for determinism, and it's only a desire, an affinity, I suppose, would point me more towards that kind of interpretation of quantum mechanics, or that kind of, a better way to put it would be a completion of quantum mechanics.
Yeah, I think. Sorry, keep going, Professor Strevens. Yeah,
that's probably about all I have to say about.
Because I see what you mean. Because I don't know what I certainly am a bit agnostic too. although deep down, I think there is some kind of determinism to existence, ontologically speaking. Although then comes, this is again where philosophy comes in. What do we mean by determinism? Like that itself is a deep philosophical question now. How is it predictability, causality? What does that mean to for something to be deterministic, let's say? Yeah, so okay. I don't know if it's fair to put you on the spot here, but I tend to come more from, in fact, the continental philosophical tradition. Like I got into philosophy more through reading people like Heidegger, Nietzsche, Kierkegaard, and it seems to me a big part of, well, one big thing in continental philosophy is that they take the idea of negation, negativity, and nothingness quite seriously. As in, for someone like, let's say, Bertrand Russell, for instance, the quintessential Anglo-American kind of analytical philosopher, the idea of nothing or zero would just be that it's nothing, it's zero. Whereas I have a feeling more of a continental philosopher would even ponder and speculate on what is nothing and keep going ad infinitum, in fact. But pertaining to our conversation on science, what do you think? What role do you think does human subjectivity play in both scientific thinking, but also generally, what's the value in speculative kind of subjective thinking? Let's say in philosophy. What are your views on that in general?
Well, I have to say, I'm not sure I have too many views about that.
Oh no, so again, as I told you, because you got carte blanche to just say what you want. Yeah.
Sure. Okay. Well, I am a scientific philosopher, I suppose, and the picture of the universe that science gives us is one where the subject is very much out there in the very same universe that we're studying using our science. So, although there's no question that being a subject is an extremely distinctive thing that has a very different feel than the rest of the world outside us feels. But what it's like to be me as a subject is something that's very different from what it's like to be this bottle over here or whatever. Yeah. Nevertheless, that science looks like it's promising us a kind of a worldview that where all of that special feeling will ultimately just be made sense of in the same, by using the same physical principles as we use to make sense of the bottle. So that's I feel like I am in the grip of that picture without really having much idea of how to use the physical principles to make sense of what it's like to be a thinking, conscious, agential being in charge of at least some small parts of my own destiny.
Yeah, I mean, because I feel like the question of subjectivity is coming up again amidst the kind of AI revolution. People are beginning to wonder what does it mean to be a self-conscious being, which is why I think it is obviously a philosophical question, but I think it should even be a scientific question to a certain extent. What is
subjectivity? Yeah, well, I suppose you take those kind of incipient efforts to make sense of subjectivity using the picture that science has given us of the world. So trying to give stories, I mean, philosophers do this as much as scientists do, principles that tell you what meaning is, what representation is, and even ultimately what it is for something to be conscious. There's a kind of clearly a research program there to take those same principles and apply them to AIs and say, is an AI thinking? Well, is it representing something? Well, we have a theory of what it is to represent something that we feel explains what it is for us to represent things, to have beliefs about the world. Let's just apply it to the AI. And because we think of because on the scientific picture, we think of ourselves as physical systems, these principles are well geared towards being applied to physical systems, and so they can be applied easily enough to the AIs. So there's the scientific world picture makes this project that you're talking about, well, not easy, but obviously feasible. Whereas if you have a rather different way of thinking about subjectivity, where it really can only be grasped from the inside, then it's hard to see how you would even get started asking whether an AI has subjectivity, except to make observations like, well, it sure does seem alive.
Yeah, yeah, like the famous what's the experiment where by the computer scientist who suggests how to
Turing,
Turing test. That's it. Yeah, the Turing
yeah,
test.
Turing,
Yes, I
yeah,
totally forgot about Alan Turing
exactly,
his
yeah.
test. Yeah.
So, right, so we can apply the Turing test to AIs as we do to other people, but you could still be skeptical even if something that passes the test. And I think the large language models actually kind of
In
will,
fact, yes.
will tend
Yeah.
to encourage people to be
Yeah.
skeptical.
Yeah. Oh, I would certainly say most LLMs would pass the Turing test. I mean, some of them are bizarre as to how good they. And I would
Yeah,
even argue that in a, like an ironic way, the reason they may fail the test is because they seem a bit too perfect. Like the
yeah.
way the answers are laid out, it's not how a human being would respond to a given question with such eloquence and everything is cogent.
Well,
Uh,
they're also a little bit kind of blank and plodding because a certain sort of characterlessness or affectlessness.
yes, more like a kind of like a sociopath. It's like you're talking to a
Yeah.
sociopath.
Well, I was gonna say, just if somebody writing a corporate memo.
Some of them tend to be sociopaths, unfortunately. But that's a whole other
One
conversation.
thing that the whole AI thing makes me one one thought it's really prompted in me is that a lot of what modern society has done to human beings is to make them like LLMs, make them like AIs. So
Yes.
when the way my students sometimes when they're phoning it in, write answers to their papers, or the way that people who work in companies write their memos, they've kind of been trained to do it in a certain kind of formulaic way, which is very much the way that these AIs are kind of learning to do what they do. And there's
Yeah.
a certain similarity between that kind of just stringing together the sentences um, to sound plausible and convincing, whether it's being done by my students, by someone who's sort of doing their job with less than 100% passion, and by ChatGPT.
Yeah. In fact,
To what extent? Yeah, go.
yeah, no, that's a very perspicacious point, Michael, because I don't know if you're familiar with a philosopher called Sean Kelly. He studied under Hubert Dreyfus. Kind of,
Oh
he
yeah.
works in the continental existentialist
Mhm.
tradition. And he made a really good point in a podcast I listened to a couple of months ago, or probably like a year ago now, that we have this question about AI and AGI, computers becoming, or let's call it AI agents, are they becoming more like human subjects? And
Mhm.
his whole point was, well, it could be that, but it could also be that more human beings are becoming more like computers or like AI, as in
All right.
we're so immersed in the world of technology and all these LLMs and all these chatbots and whatnot that we end up becoming and talking and behaving like AI agents, because it's kind of we have this assumption that there's a human nature and this is how we act and behave,
Mhm.
but then in fact I would say there's a lot of scientific evidence that perhaps negate that idea that there is a human nature there, that human nature is quite fluid and dynamic.
Yeah. Although I would put it down not so much to modern information technology as to more kind of a kind of social technology. The way we get by in the world often is just to kind of emulate what's going on around us. So we're doing the same thing that the LLMs are doing. They're kind of seeing what everyone else is doing and creating some kind of facsimile of that, sort of getting the patterns basically right.
See
And
that.
so are we when we're dealing with the social complexity of the modern world, when we're not just living in the little groups that humans lived in for so long, well, as far
Yeah,
as we can
yeah.
tell. So it kind of encourages a way of dealing with the incredible complications of the world, of a world where you have to
Globalized
interact
world.
with
Yeah.
thousands of people, that the coping strategy is the same as the chat GPT strategy.
I see what you're saying. So what you're saying is it's not that we are becoming more like LLMs, or AIs, but rather both AI agents and human subjects are following this kind of meta rule or meta pattern of what it's
Yeah.
like to be in. Interesting. I see that. Fascinating stuff. Okay, Professor. So, and forgive me if I'm putting you on the spot, but I had this opportunity, so I want to ask you this question.
All
Uh,
right then.
it's again on human subjectivity. Are you familiar with a philosopher? He's a continental philosopher called Slavoj Žižek.
Mhm.
You're probably familiar, right? So I'm a big fan of his work.
Mhm.
And just on a side note, when you spoke, when I read your book for the first time, and when you kind of introduced the idea of the iron rule, my mind or my head straight away went to what he talks about, this thing called the socio-symbolic order. And he kind of defines that as a virtual category where it's not that it's a subjective stance that exists in the human in a certain in an individual human psyche, but rather he views it as this kind of virtual reality. It's not something material or substantial, but as a result of individual human beings interacting socially in the world, there's like this symbolic order that emerges, and
Mhm.
that's the way I view to in many ways the iron rule of explanation, where no, it's not someone somewhere said this is what the iron rule is, nor is it written down in, like, I don't know, from God above saying this is what the iron rule is. It kind of like emerges from our social interactions. But I wonder if I could read a little excerpt from his book, Absolute Recoil, which is like a book on Hegel. And I wonder if
Mhm.
I could get your kind of reaction to it, if
Mhm.
that's okay. So this is from Absolute Recoil, and this is on the human subject. And here's what he says, right? And given that you're more of an analytical philosopher, I'm really curious to hear your thoughts on this. He says, the subject is the immense absolute power of negativity, the power of introducing a gap or cut into the given immediate substantial unity, the power of differentiating, of abstracting, of tearing apart, and treating as self-standing what in reality is part of an organic unity.
Mhm.
So, what are your like initial views on like on that kind of statement?
Well, just going on what you read, that sounds a little bit along the lines of the view I was myself promoting a few minutes ago when I was saying that it seems like the subjectivity as the way we experience it is being really making us completely different and in a certain important way separate from the world is a kind of a construction. The reality is something more like the scientific world picture, where we're systems like bottles and telescopes and AIs and so on. I'm not sure if that's what Zizek actually means by that passage, but it sounds somewhat in accordance with it.
I see, yeah, because I think Zizek is certainly not unlike certain continental philosophers. He doesn't play the whole postmodernist game where I hate that,
Mm-hmm.
honestly. Like, oh, it's
Mm-hmm.
just another episteme, it's just another domain of way of viewing the world. The question I guess he'll pose, if I could speak for him, would be, in this world of objects, in a world of, as you said, bottles, atoms, whatever you may call it, how is it that subjectivity emerges? As in, what causes this us beings to emerge where we suddenly become self-conscious and then we start abstracting out and doing such things? Have you got any views on that?
So it sounded like his, at least the view he was suggesting in those sentences, was it's almost like just a kind of an arbitrary cut that puts me on one side of a
Exactly.
barrier and the world
Yes,
on the other
arbitrary
side.
cut. That's it. Yeah, but how is it that
Yeah,
it's us, the subject,
it
and then
seems.
the world out there? It's a weird thing because I'm sure this pen doesn't feel that. It doesn't feel that it's the pen and then the world out there.
Yeah, it seems. I mean, I feel that it's not. It doesn't seem like it's something we do to the world. It seems like something that gets foisted on us, this subjectivity. We just come into the world kind of, and it impresses itself on us in this way that makes us very much the perceiver, and then of course soon enough the agent. And we're not choosing it. We're just thrust into that position as though the cut, if we're just going along with the cut thing, as though the cut is made for us by well, I don't know. You mentioned evolutionary theory. I didn't quite get to answer that question. I realized, but of course we can't talk about everything.
Fair enough.
Maybe the cut is, as it were, a sort of part of our inheritance as human beings, or as some broader class of beings. Maybe large numbers of mammals have the same cut, and maybe the class is even larger than that. Who knows? And
Yeah.
it's a kind of a it becomes, even if we're just another system, it's very important to being to dealing with the world, to being a effective agent in the world, to conceive of yourself as an effective agent, not in an intellectualized way, but just to kind of face the world as a series of decisions to be made about actions to be performed, which is a very different way of thinking about yourself than the scientific picture where, like any physical system, you're just subject to the laws of nature and the virtue of your physical makeup. So this whole psychology of agency is something that's prepared for us, if you like, from the very beginning, from birth, and we just step into it whether we like it or not, and find ourselves in what appears to be at least the captain's seat.
Certainly. Now, Professor, I think Žižek would agree with you, because what's interesting is he kind of views human subjectivity the same way. He's like, oh, we don't choose to be human subjects. He even says, in fact, it's kind of a hellish experience. Jean-Paul Sartre said that we're condemned to be free, where we're in this world and now we have to choose. Whereas the scientific worldview, if everything were just objects, then those objects, that we don't prescribe any kind of agency onto them. But then again, here's where these things get interesting. If we build AGI, wouldn't we be prescribing this kind of subjectivity onto AGIs? And suddenly, at one point, the quote unquote the singularity, now the AGI is going to have this cut, the arbitrary cut in reality, where it feels it's me and then the world out there.
Well, his reason to think no, actually, because
okay,
if you imagine that AGI will so actually, I think a lot of people are skeptical about this.
Oh, yeah, so am I. Yeah,
who are big AI proponents. But if you imagine it actually working like ChatGPT, in an LLM way, that in a way that's a very different way of dealing with the complexity of the world and being as I said, in a sort of effective in the world, than sort of feeling yourself as thinking of yourself as a decision maker who's reacting to discrete events by deciding to act in certain ways. Something like ChatGPT is, this is a bit metaphorical, I suppose, but it's not really thinking in that one-dimensional serial way. Rather, it's kind of thinking what word comes next, what action comes next, based on a million different considerations. And it might be that even if such a intellect could be conscious, it wouldn't experience itself as an agent. Maybe it would just experience itself as a prediction machine. It would be like rather than thinking of itself as something that was free to perform actions, it would just be something that thought of itself as this kind of pure predictor of what the next best thing is.
Yeah. It's funny. I wonder if that's what God is ultimately. The problem with there's this theological question. I think it was Augustine who said that. But the one limitation God has is that God has no limitations. So that's what we humans have over God, where we in fact feel that we're here now. We need to predict. We don't really know what the future holds, and we need to act and kind of live in this world. But no,
so our agency may come from a sort of a very narrowness.
Yes, exactly. Come from our affinity in that sense.
Cognitive simplicity.
Yeah. But thank you, Professor, for humoring me with that. I really appreciate you letting me ask you about Žižek, because I know like a lot especially people like Noam Chomsky are very critical of like continental philosophy and kind of European the way of thinking. But I find there's great depth and insight into their way of thinking too. But I'm cognizant of the time, Michael. So before we end the podcast, I guess just as a concluding question, what other projects have you got in your pipeline? I'm always curious to hear what other books are upcoming works are you planning?
Well, actually, recently I've been thinking about cognitive development. That is, how children get from being having fairly limited conceptual inventory to having the ability that we adults have to think about all sorts of things in the world, like numbers, for example, in particular. I've always been a bit, I guess I got interested in this from being a philosopher of science and where new concepts come from. But the place where you can study new concepts coming along every day is in young children. So I've been spending quite a bit of time reading and talking to developmental psychologists and trying out some of my own ideas about novel concepts on them. So that's where I am right now.
Fascinating.
Very different place, very different from what I wrote about in
The
the
previous book, right? Yeah.
Quite,
No, but
quite
still,
project.
you do
The
have a
one that's been
background.
going on for about as long as that one has.
Yeah, because you have been writing on the philosophical, or you've got some work published on the philosophical applications of cognitive science. So I can see how that can be something quite interesting. And again, I mean, who knows? You can probably, being a philosopher, you can do this. Maybe make connections to even AI agents, the development of an AI agent, or I don't know.
This takes us
Very
back to
speculative, but
your
yeah,
very first question. I became a philosopher so I could do all
exactly.
this
Yeah,
and
yeah.
call it an honest day's work.
There you go. I mean, in fact, I, like yourself, I studied computer science too. I'm a software engineer. My day job is that.
Uh-huh.
Eventually, my goal is to go become an academic and kind of, probably go into. I want to study AI and cog side, but then maybe eventually maybe into philosophy. Who knows?
Yeah.
But thank you very much, Professor Strevens, for your time. I really appreciate it. I thoroughly enjoyed reading your book. In fact, I read it twice. And as I said, I think now if anyone's going to ask from me about the philosophy of science, I'll just give them your book and read chapter one. You'll get a good education on that. So thank you, Michael.
Well, that was a lot of fun. I really enjoyed talking.